Here's a couple of homework problem helps that I'm just going to work these out for you. These are from page 333. I'm going to work out number 2, and then we're going to take a look at number 6. So the directions tell us to use the rational root theorem to list all possible rational roots for the polynomial equation. So the way I use the rational root theorem is I look at the constant, which in this case is -6, and I write in the numerator of the fraction all of the factors of -6, plus minus 1, plus minus 2, plus minus 3, and plus minus 6. And then in the denominator of this fraction, I list all the factors of the lead coefficient, which in this case is 1. So the denominator will be plus minus 1. So the possible rational roots, since I'm essentially dividing by 1, are these 8 numbers, positive and negative, 1, 2, 3, and 6. Okay, so to find actual rational roots, I'm going to use synthetic division with these numbers. Just going to make a list. If you notice the pattern that I showed you earlier, that really serves as quite a very good shortcut, and that means the pattern is that if our coefficients 1, 4, and 1, if they multiply together to equal the constant, then it makes finding the rational zero very easy. Unfortunately, that pattern doesn't hold true here, so I'm just going to have to do some testing using synthetic division. Okay, so notice I put the coefficients across the top and the possible rational roots along the side. All right, so let's begin. Bring down the 1, multiply 1 times 1, and then add 1 plus 4 is 5. All right, multiply 5 times 1 is 5, plus 1 is 6. Multiply 6 times 1 is 6, plus -6 is 0. It's very nice when we get our rational zero right off the bat. One of our 3 solutions that we're going to have is the number 1. So the way I'm going to have you find the other 2 solutions is to take these numbers that represent constant, linear coefficient, quadratic coefficient, just like we learned with synthetic division, make an equation out of these numbers, let that equal 0, and then solve. And in this particular case, we don't have to use the quadratic formula. I mean, you could if you wanted to, but as it turns out, this actually factors. There are factors of positive 6 that add up to positive 5, positive 3, positive 2. So my solutions, the other 2 solutions, will be -3 and -2. So my overall final answer, the 3 solutions to this cubic polynomial are positive 1, -3, and -2. All right, so easy enough. Let's try another one. Okay, this is a little different than what we did in class. It's actually been put into this by mistake, but I'm going to show you really 2 different ways of coming up with the solution. We'll use what we did today in class, and then we'll use an alternative way. So to start with, let's use our rational root theorem to come up with the possible rational roots. So let's make a list of all of the factors of -15. Plus minus 1, plus minus 3, plus minus 5, plus minus 15. All over factors of the lead coefficient, plus minus 1. So really the factors of, or the possible rational roots, are these 8 numbers in the numerator since we're dividing by 1. Okay, so let's make a list. 1, -1, 3, -3, 5, -5, 15, -15, and across the top we're going to do 1. Notice we jumped over the cubic term, so we're going to plug in 0. 2, no constant term, 0, and then negative 15. Okay, so let's start the process. Bring down the 1, multiply, and then add. Multiply, 1 times 1, then add, plus 2 is 3. 3 plus 0 is 3. Now at this point, I know I'm not going to get a 0 remainder, so let's move on to the next number. Negative 1 plus 0 is negative 1. Negative 1 times negative 1 is 1, plus 2 is 3. This would give you negative 3 plus 0. I'm not going to get a 0 there, so just going to keep going. I'm just marking those off because they didn't work. All right, 3 plus 0 is 3. 9 plus 2 is 11. 33 plus 0. And 99 plus negative 15, not even close, so let's keep going. Negative 3 plus 0. 9 plus 2. Negative 33 plus 0, not even close. All right, continue on. 5 plus 0, 25 plus 2, 27 times 5, 27 times 5, 25 times 5 is 125, so I believe that's 135, but in any case, we know we're not going to get 0. All right, negative 5 plus 0, 25 plus 2. We're going to get the same thing here, except this is going to be negative 35. You kind of see the pattern. All right, so far we're striking out. 15 plus 0. I'm going to save you a little bit of time. All the way through, as we check these, none of them give us a 0 remainder. So what does that tell us? Well, it tells us there are no rational roots. Doesn't mean there aren't any roots. It just means that none of them are rational. Okay, so the table here doesn't help us. Well, what about this? Back in section 6.4, we learned how to solve these quartic trinomials using factoring. There are factors of negative 15 that add up to positive 2. We're going to use 2 quadratic binomials. Okay, so the factors of negative 15 that add up to positive 2 are positive 5 and negative 3. So if I solve each one of these, I get x squared equals negative 5. So x is plus minus I root 5. Okay, over here I get x squared equals 3. X equals plus minus the square root of 3. So I got all 4 solutions, but none of them are rational numbers. So using the rational root test basically told me that there are no rational roots. Okay, so it says to, in the directions, it says to find the number of rational roots. Well, there aren't any, but we do have 4 roots. The square root of 3 is an irrational number, and then of course this is a complex number. So that's your answer for number 6. Okay, so I hope that helps, and there's a separate video that has a couple of problems on page 337. I will tell you this, I showed you on that separate video how to do number 14, so you can watch that. You're going to do number 13 in very much the same way. So I showed you 14 working out. Number 13 you should also solve by factoring, because the directions just say to find the zeros. They're a little bit different directions than what you had in the previous section, where you had to list all the possible rational roots and then determine how many actual rational roots. So just solve 13 and 14 on page 337, using factoring like you learned in section 6.4. And let me know if you have any questions.